Hello students, welcome to Educate. We are going to start with the chapter Wave Optics of class 12 physics. So let's see the basic concepts. The first one is wavefront. Wavefront, suppose this is a point source here and we consider, you can consider this thing from here. So what is wavefront? You can easily understand. Suppose this is a point source, then rays will come out in all directions. So at any point of time, we just locate the locus of all rays. So we will find a circle, right? After some time again, if we locate the locus of all rays, then we will get another circle. So these are wave fronts, right? So if you observe the definition, a wavefront is defined as the continuous locus of all such points or particles of the medium which are vibrating in the same phase, right? So consider this is extended source. So what type wavefront will be there? So this is extended source. So rays will come out in all directions. So if we plot or if we draw the wavefront, so we will get like a cylinder. Here at end points it is shown. So this is one ray, another ray, third ray, fourth ray, like this. And then at certain time t, the locus is joined, so that forms a circle, and this is how there will be collection of circles one over other. So we can say that it is forming a cylinder. So here this will be cylindrical wavefront. Now if source is very far away, in that case rays will be parallel, then we will get wavefront like this. So here these are parallel wavefronts. Here if you observe, all rays are going to meet at one point. So you can say that these are the wavefronts and this is converging type. So since they are meeting at one point, and here this is just opposite. The rays are going like this, so these are the wavefronts. This will be diverging type. So what you have observed here? So first you have seen the definition that a wavefront is defined as the continuous locus of all such points of the medium which are vibrating in the same phase. So they must vibrate in same phase. And then we have seen different type of wavefronts, like this is a spherical wavefront. Here there is point source and rays are coming in all directions. And then we have located the locus and hence we have got the circles. Here we have considered this extended source. So wavefront will be of cylindrical type. Then in this case what we have seen, that rays are coming from a distant source. So wavefronts will be like plane wavefront. And in this case what you have observed, the rays are converging at one point. So these are the wavefronts. So these are converging wavefront. Here what is happening? Rays are going like this. So these are the wavefronts and this is diverging type wavefront. Now if you observe the direction of rays and wavefront, they will be perpendicular. So here note number 1, it says rays are perpendicular to wavefront. Note number 2, the time taken for light to travel from one wavefront to other is the same along any ray. So if you observe from here to here, whatever time light takes to reach here or from here to here, so it will remain same. Now we are going to see Huygens principle. Huygens principle is, it is the basis of wave theory of light. According to Huygens principle, each point on wavefront is a source of secondary waves, right? So if you consider any wavefront here, so suppose you consider this point or this point or this point or here this point, so it will again behave like a light source. So here each point on a wavefront is a source of secondary waves which add up to give a wavefront at any later time. Then we see the assumptions. Assumptions. Each point on a wavefront acts as a fresh source of new disturbance called secondary waves or wavelets, right? Then next point is the secondary wavelets spread out in all directions with the speed of light in given medium. You have seen first point and this is second point. Now let's go to third point. The new wavefront at any later time is given by the forward envelope, that is tangential surface in the forward direction of the secondary wavelets at that time. And one important point, that no backward wavefront is possible. Amplitude of secondary wavelets is proportional to 1 plus cos theta. If you move backward, then what will happen? Theta will become 180 degree and cos 180 is minus 1. So 1 plus minus 1 will give 0. So that is why we say that backward wavefront is not possible. Here theta is the angle between the ray at the point of consideration and the direction of secondary wavelets. For a backward wavefront, theta is pi, and so the resulting amplitude will be 0. So you have understood. Now we are going to see the reflection on the basis of wave theory. So you know that we need a reflecting surface. So here BC is a reflecting surface. These are two rays that are incident. So at this point we draw incident wavefront, right? This angle is I, right? This BA will be incident wavefront. And when this point travels to this point, till then this point travels to this point, then again we draw another wavefront, this CD. This is a reflected wavefront. Now what is our purpose? Our purpose is to prove that I equal to R. So it is very obvious. Here this is perpendicular and here this is perpendicular, so both these angles are 90 degree, right? And since light is traveling in same medium, so from here to here, whatever time and whatever distance light has traveled, the same will be true for this. Means you can say AC equal to BD. Correct? And this is common to both, means hypotenuse. So from RHS congruence conditions, you can say that these two triangles, triangle ABC and triangle BDC, will be congruent, and if they are congruent, then this angle equal to this angle up to here, ABC, and angle DCB will be equal, that is sine, this is I equal to R. So angle of incidence equal to angle of reflection. So this is how thing is proved. The same thing is explained here. BD, that portion, BD means from here to here, speed of light is c, and suppose time taken is delta t. So this BD will be c times delta t, or just write t. Similarly, AC, medium is same, so speed of light is c, so A to C. So c times time taken is t, so this is ct. So both BD and AC will be equal, as I have already discussed, and angle A equal to angle T. These two are 90 degree because wavefront is always perpendicular to the direction of the ray, correct? So BC equal to BC, that is common side. So these two triangles will be congruent, and if they are congruent, then angle I will be angle R, angle I will be equal to angle R. So this is how we have proved. Also, since the incident ray SB, if you observe here, so this is incident ray. Also, since the incident ray SB, normal BN, here there is normal BN, reflected ray BD, if you observe here, this is BD, are respectively perpendicular to the incident wavefront AB, the reflecting surface XY, and a reflected wavefront CD, all of which are perpendicular to the plane of paper. Therefore, they lie in the same plane of paper. So, you know that there are two laws of reflection. Both are proved here by using the concept of wavefront. Correct? Now, we are going to see Another thing, that is refraction on the basis of wave theory. So refraction, you understand that when a light ray enters from one medium to another, then its speed changes, and if medium is denser, then speed will decrease. So here we are going to consider these are two rays. This is interface, this is denser medium whose refractive index is mu2, and here refractive index is mu1. Now speed in this medium is say v1, in this medium say speed is v2. Here what is our purpose? Here our purpose is to find Snell's law, that is sin I upon sin r equal to refractive index. So let's see how. So here what we see, this is incident ray, and here we have drawn incident wavefront. This is another ray. Now when this ray reaches at point A, this ray reaches at point B. Exactly why this is wavefront. Now during time t, this point travels from from here to here. So distance traveled by light particle will be equal to bc in time t, that is v1t. Similarly, here speed will become v2, time is same, so this distance will be bd will be v2t, correct? And this angle is I, and here we have drawn this, we have joined this point and this point, we have got this refracted wavefront, right? So this is incident wavefront, this is a refracted wavefront. This angle is I, this angle is R. Now we have to consider sin I and sin R. So for getting sin I, this is perpendicular. So this BC will be perpendicular, and this point from here to here AC will be hypotenuse. Similarly for this, in this triangle ACD, perpendicular will be this AD, that is V2T, and hypotenuse will remain same AC. So we write this here, AB is incident wavefront and CD is a refracted wavefront. Angle I is the angle of incidence and angle R is the angle of refraction. And in triangle ABC, as I told you, and triangle ADC, angle B equal to angle D. You remember that wavefront always makes a 90-degree angle with the ray. So here this is wavefront, this is a ray, so this is 90. These two angles are 90-degree, correct? So the same thing is written here. Now our concern is to get sin I upon sin R. So sin I perpendicular, as I told you, this V1T will be perpendicular and AC will be hypotenuse. So V1T divided by AC divided by perpendicular will be V2T divided by AC. So here AC will cancel out, T upon T will cancel out, then V1 upon V2 will be left. Now if you take refractive index of this medium as mu1, so we write mu1 times sin I equal to refractive index of this medium is mu2 times sin R. So this gives V1 upon V2, right? So sin I upon sin R will give mu2 upon mu1, and mu2 upon mu1 is the refractive index of second medium with respect to first medium. So V1 upon V2 is mu, which is Snell's law. So I think you have understood up to here. Now there is another concept, effect on wavelength, frequency and speed during refraction. So what happens? Frequency is the internal property of wave, so it will not change, but wavelength and speed will change. So when light enters from one medium to another, suppose medium is having a refractive index mu, then speed in that medium will be given by V equal to C upon mu, right? And definitely if medium is denser, so its the refractive index will be more than 1, hence the speed will be less than that of speed of light in vacuum. Now frequency, as I told you, there is no change. Wavelength will change. Wavelength will get divided by refractive index. Speed of light in medium is less than the speed of light in vacuum. Now we are going to see one question. Question says monochromatic light of wavelength 589 nanometer is incident from air on the water surface. Find lambda dash, nu dash and v dash of reflected, refracted. You are given refractive index of water with respect to air is 4 by 3. So it is very simple. So here what happens? Frequency will not change, be it reflected or refracted. In case of reflected light, the speed and wavelength will also remain same. But in case of refracted light, as I told you, speed will change, frequency will remain intact, and wavelength will also change. The both means wavelength and velocity will be obtained by dividing refractive index. Means if this is lambda is wavelength in given medium, sorry, not in air, and mu is a refractive index of the medium in which light enters, then lambda dash will be lambda upon mu. Similarly, speed in that medium in which light is entering, whose refractive index is mu, so it will be c upon mu. And the frequency, as I told you, being internal property, does not change. Now, let's see another question. Here, what is the geometrical shape of wavefront in each case? Light diverging from a point source. I have told you that when light diverges, then we draw the wavefront. So, in case of diverging, it will be spherical. Then second point, it light emerging from a convex lens. So when light comes out from a convex lens, then the rays will become parallel. So we can get plane wavefront. We have already studied when light rays are parallel. In that case, we draw the wavefront. Okay, then portion of the wavefront of light from a distant star. If light is coming from distant star, definitely the rays will be parallel. And if rays are parallel, in that case, we get plane wavefront. We have already studied about these concepts. That is why I am not drawing the diagram. Now, let's see next question. The refractive index of glass is 1.5. What is the speed of light in glass? So, if you remember, I told you that refractive index is ratio of speed of light in air to speed of light in medium. So, here refractive index is given 1.5 and we have to find out the speed v. So, c upon v equal to mu. C is given 3 into 10 power 8 and mu is given 1.5. So, just divide it to get v. So, v will be equal to 2 into 10 power 8 meter per second. Next question says, is the speed of light in glass independent of the color of light? No. Be very careful. Since speed is given by v equal to c upon mu and mu depends on wavelength of light. If you remember the spectrum, you have seen that wavelength of red color is highest, right? So if red color has highest wavelength, then its mu will be the least, right? If mu will be the least, then v will be more. Similarly, if you consider violet color, whose wavelength is the least out of those 7, so definitely its mu will be larger. When mu will be larger, then what happens about v? So v will be, since mu is larger, then v will be lesser. So this is basic concept. Now further, let's see next point. Light of wavelength 5000 angstrom falls on a plane reflecting surface. What are the wavelength and the frequency of the reflected wave? For what angle of incidence is the reflected ray normal to incident ray? So here situation is given. Light of wavelength 5000 angstrom falls on a plane reflecting surface. What are the wavelength and frequency of the reflected wave? For what angle of incidence is the reflected ray normal to the incident ray? So here what is happening? In case of reflection, no change will occur, so everything will remain same. V will remain same, wavelength will remain same, frequency does not change, that you know very well, and the two should be perpendicular. For that, theta must be 45 degree. You can easily analyze. Now, let's see the behavior of prism, lens and mirror. So in case of prism, what happens? These are two parallel rays. This is a prism. Now we assume this as incident wavefront. Now what happens? For this ray, there is very less obstruction inside the prism. That is why it will be slowed down for a moment, and then again it will travel in air. So till the time this ray reaches here, this ray will reach here, because here this ray has to travel for a longer period inside the prism, so speed will be slowed. So that is why this path will be less than this path, right? So during time t, the points, the source, or you can say the source that is vibrating and that is moving, or you can say photon. So if it reaches here, then this will reach up to here. So this is a refracted wavefront. So you have to remember why this type of wavefront, why there is bending here. So here it is obvious that in this case, this ray is traveling for lesser time inside the glass prism. So speed is slowed down momentarily, whereas in this case, the time taken to travel inside the glass is larger. That is why this path will be shorter. Correct? Now consider the case of lens. So these are three rays. This is lens of converging type. So here we draw incident wavefront, and then since thickness of lens is larger at this point, so this distance will be the least, and this will bend like this, this will bend like this. So this is the point where these rays are converging. So here we can plot this type of refracted wavefront, right? Another wavefront can also be plotted or drawn. Then we consider concave mirror. So concave mirror, you know, these are parallel rays. So here we draw incident wavefront. Now after traveling, after reflection from mirror, these rays are meeting at focus. So we can draw this type of wavefront, and this is called a reflected wavefront, right? So there are more questions we will see in the next video. Thank you for watching. Team Educate.